Here you see the RT7800 host board. It can be used for emulating various USB Type-C power delivery load conditions. It has an onboard RT7800 USB port controller with 8 push-button switches for selecting different power profiles. The dip switches can be used for selecting different modes, like fixed voltage profile or programmable power supply modes. It also supports legacy charging protocols like QC 2.0 and QC 3.0. The separate board is a USB I2C bridge, which can be used to connect the board to your PC for programming different firmware into the RT7800 IC, in which case you can also control the load board via your PC. The host board can be powered from the USB Type-C V bus, but for some operation modes it is better to power it from a separate 5V supply. I will show you how the host board is used by connecting it to this RTQ7880 USB PD 60W car charger evaluation board. This evaluation board can provide 5, 9, 12, 15 and 20V at 3A max load, and can also support PPS 3.3V to 21V at 3A load. I will connect a 12V 5A supply to the RTQ7880 evaluation board input. I will also measure the V-bus output of this board and the V-bus input of the host board. I will connect a constant current electronic load to the host board load pins. When applying the 12V supply, but the cables are not connected, the V-bus is off. When I now connect the Type-C cables, the car charger board provides the default 5V V-bus. You can see that at zero load, the V-bus at the charger board output and the host board input is the same. When I now start to increase the load, you can see that the charger board V-bus increases to compensate for the voltage drop across the cable, in order to keep the V-bus voltage at the host board input nearly constant. At 3A load, the charger board applies around 300 mV extra voltage for the cable drop compensation. The host board has interrogated the RTQ7880 car charger board to check its source capabilities. Depending on these source capabilities, buttons 1 through 7 will request new power profiles. In this case, button 1 selects 5V, button 2 9V, button 3 12V, button 4 15V, and button 5 the 20V profile. Before selecting 20V, I will increase the input voltage a bit to avoid exceeding my power supply 5A current limit. You can see that the cable compensation keeps the V-bus voltage at the host board input close to its nominal value. By selecting different dip switch setting, you can set the host board in programmable power supply mode. Because PPS starts around 3.4V, this voltage is too low to power the host board from the V-bus. So I apply an external 5V to the host board supply. Now we can connect the cables again. The system default will start at 5V again. Button 1 and 2 will now select the lowest PPS voltage. Button 3 will increase the PPS voltage by 1 step, and button 4 will decrease the PPS voltage by 1 step. Button 5 and button 6 will increase and decrease the PPS current limit in steps. Button 7 will select the maximum PPS voltage and current, which is 21V with 3A current limit. You can see that when you increase the current, the PPS mode will not add any cable compensation, as in this mode the host board will purely request voltage and currents from the source. The PPS current limit is also very precise. You can easily test this with a variable resistor load. I select the 21 3A PPS profile and slowly reduce the load resistance. You can see that when the 3A current limit is reached, the voltage starts dropping and the system operates in constant current mode. In this mode, The undervoltage protection is set at 60% of the nominal V-bus voltage. So undervoltage protection will happen around 12 volt, after which the system shuts down and automatically restarts at the default 5 volts. Let's reprogram the host board to make it a PC-controlled version. I connect the I2C bridge to my PC USB port. The board is now powered from the USB supply, so you don't need the separate 5 volt supply. We will run the RT7800 MTP programming executable, connect to the MCU, verify the IC connected and then load the firmware for PC control. The RT7800 MTP memory is now programmed and verified. Now we can control the host board from the PC via the demo panel program. Initially, it shows that the cable is detached. We'll connect it to the RTQ car charger board again. You can see that the demo panel confirms the connection. You can now check the source capabilities of the charger board, which shows all the fixed power profiles and the PPS power profile. By clicking the Sync Capability button, you can see that this host board can request up to 100 watts of power, basically covering the whole USB PD power range. In the Power Request menu, you can now select any of the power profiles of the charger board. Let's choose the PPS profile. We can now select any voltage and current within the PPS range. For example, 8 volt and 2 ampere current limit. The demo panel can also request voltage and current sense information from the source, but this must be supported by the charger board firmware. The 60 watt charger board does not support it, but I can swap the 60 watt charger board for a 45 watt firmware version that supports this. Now you can see that the host board can request the sensed voltage and current from the charger board and display the values in the menu.